Okay, in this one I wanted to go over um, a classical mechanics topic, which is simple harmonic motion, and specifically simple harmonic oscillators. So let's consider a spring like this with a certain mass. I'll call that M. And let's say you apply a force in the downward direction. So we'll call that F push. Well, we can say that there's a natural tendency um, for the spring to go back to a point of equilibrium. So that means that there's a force in the opposite direction applied upwards, and that force is proportional to negative kx. Right? It's in the opposite direction. That's why there's negative. Where k is the spring constant, which is dependent on the specific type of spring and its materials. So yeah, so essentially what happens is when you apply a force, the restoring force tries to get the spring back to a point of equilibrium, which is its natural length, and then every time it tries to do that, it overshoots this point of equilibrium, and this is obviously assuming that there's no friction, which is why it's simple harmonic motion. So if we want to graph the position versus time of this system, it would look something like this. So consider your x-axis, and then your t-axis, so x, t. So it would be a sinusoidal wave, right? You have your 1 and negative 1, and you start with some position, and then you have this sinusoidal motion that repeats, this oscillatory periodic motion. Obviously, it doesn't look that well drawn, but I think you get the idea, right? I mean, obviously, this is supposed to be much higher, but yeah. So the idea is that it continuously oscillates back and forth. But really, we know that there's friction in the system, and the type of mechanical system you would deal with the springs would look something like this. So you'd have, again, your x and t axes, and you'd have some position, and then you'd start your oscillatory motion, but every time you do it would decrease in your wave. Well, your wavelength would remain constant, but your amplitude would decrease. So this is called damped harmonic motion, because each oscillation gets smaller and smaller until the spring is back to a point of equilibrium. So really, what we kind of want to do is represent the simple harmonic motion with as a function of x, and with the position. So the reason why we're not going through the damped harmonic motion is because it requires differential equations, and that's more of a college physics topic. So really, we want to develop an equation that describes x, or position, as a function of time, and well, we want to find what that's equal to. So the way we would attempt to derive such an equation is through a reference circle. There's multiple ways. I believe you can do it through calculus, but I don't know if that's going to be necessary at the moment. So consider a circle, and then consider its y and x axes that bisect the circle into equal quarters, but it's not in this case, but I tried, so that's all that matters. So really, when you're considering a wave, you need to consider a mass. So we're going to consider some mass m moving at some angular velocity or angular speed or frequency omega. So really, when the timer starts, when the spring begins its oscillatory motion, the time is 0. T equals 0. So at that time, you start somewhere in this wave. You could be starting here, you could be starting here, or you could be starting way down here. But really, a lot of times when you start with the spring motion, it isn't directly correlated with the beginning of the cosine wave, right? So really, we need to make the assumption that we're going to have some phase angle is what it's called, or phase shift or phase constant. It's where you start out with respect to the wave. So essentially you call that phi. That's the phase constant, and that's where you start out. And then after some time t passes, so t equals t, then you have moved another quantity of angle, another little bit. So we can consider that part of the angle that you moved, and that would be equivalent to omega t, right? It's equivalent to the time spent times the angular velocity. So if angular velocity is equivalent to radians per second, and time is in seconds, if we multiply those two together, these cancel out, and you're just left with radians, which is obviously a unit of like a measure of angle, where 2 pi is equivalent to 360 degrees. So really, now we can think about, well, if we have some starting angle and then some angle at which the spring moved, in relation to like a cosine wave, then the total angle would be, we'll just call it theta. Theta is equivalent to omega t plus phi, right? The sum of the two angles. So this right here, this whole piece here, would be your theta. So now what we can consider is how we can relate the cosine function, or, well, we would need to find a function that relates the position with the time. So really, remember that this is the x-axis. So let's say we draw a parallel line from, or a perpendicular line to the x-axis. So from the mass all the way down to the x-axis. So that is a perpendicular line. And well, now we have a right triangle, and you consider the radius of the circle to be the amplitude, right? Because it's the highest point from the x-axis, alright? And you can easily see that translated over into the circle. So that's some amplitude, and like we said, this is some position x, right? Some position x. And well, if this is some position x on the x-axis, then this right here, which is, it's kind of getting messy, but I think you'll see, this right here, I think you can see in brown, is the y. It's the movement on the y-axis. But really we want to talk about and a function that describes the position with the time in mind. So really you can think about the cosine, right? Because if you have the hypotenuse and the adjacent to the reference angle, which in this case is your theta, right? The sum of the two angles, then you can just use that ratio. So you'd have cosine theta is equivalent to, well, it would be your adjacent on hypotenuse. So really, we know that the hypotenuse is a amplitude, and then your adjacent is x, or the position. So we say now that cosine theta is equivalent to this x, which is the adjacent to the to this reference angle, so x, and then that's on the hypotenuse, the longest side, which is a. So really, we know that the theta is omega t plus phi, right? The sum of the starting angle, I guess, and then the angle after you move some time t. So now we can just really just plug that in. So cosine omega t plus phi is equivalent to x on a. And really we want a function of position as, or we want position to be isolated by itself, so we can simply just multiply both sides by a. And now what you get is x, I'll write as a function of time because that's really what it is. X as a function of time is equivalent to a cos omega t plus the starting angle phase shift phi. So really we have created an equation that describes the position or the displacement over over some certain time and with the amplitude and angular frequency or angular velocity in mind. So the next thing we can do is, well, if we know that if we do the adjacent on hypotenuse, we can get a function of x, right? Well, we can do a similar thing with the y-axis. So really, you need to consider another function that considers the amplitude and this height, this side that would be opposite the angle, the reference angle. So really, we need to use sine. So we say that sine of theta is equivalent to the opposite on the hypotenuse. So yeah. Okay, so sine of theta is then equivalent to, well, we're using this reference angle, so the opposite would be this y. So y on, again, the hypotenuse remains the same, so that's a. And again, we kind of just do the same thing. This time I'll isolate for y first, so you'd have a sine theta is equivalent to your y. So y is equivalent to now our theta, right? This theta that we had solved for a while back. So now y is equivalent to a sine of omega t plus phi. So as you can see, you get very similar equations even when you consider the y-axis or parallel to the y-axis. So anyways, let's go back to the equation as a position as a function of time. And well, if you know that the derivative of position with respect to time is equivalent to velocity, we can simply just take the derivative of this function that we generated, equation, and take its derivative and get a velocity function. And similarly, we could take the second derivative of position with respect to time, and we would get an equation that describes the acceleration. Obviously, both of them would be as a function of time. Or you could just simply take the derivative of velocity with respect to time, and you would get the acceleration as a function of time. So really, now we can just apply this to the simple harmonic oscillator the equation for it that we derived. So let me just rewrite the equation. X as a function of time is equivalent to a cos omega t plus phi. So the first thing we want to do is take the first derivative to find the velocity. So the first derivative of x prime of t is equivalent to v of t, which is equivalent to, so you could just say that it's the first derivative with respect to time. I'm going to consider it as a partial derivative with respect to t. And the reason why I'm going to consider it like that is because, well, really this is a multivariable function, right? You have you only have a two-dimensional graph, but I like to think of it as, you're holding the amplitude constant, you're holding the omega constant, you're holding the phi constant, and taking the derivative of t. So that's kind of the way I'm going to think about it. You could just think of it as the derivative. It doesn't matter really. So partial derivative with respect to t of a cos omega t plus phi. So really, what we need to do is we have to recognize that we have an inside function. So that's the outside. Mixing things up here. So that's the outside function, and then the one in the brackets is the inside function. So really, now what we need to see is that we can simply just apply the chain rule, right? The chain rule states that we take the derivative of the outside, we multiply by the same inside function, and then times the derivative of the outside functions. So you essentially do it in a way that the du's cancel out and you just get dy dx. So really now, we can just apply that. So the derivative of a cos is just going to be where a is constant, right? We're not taking the derivative of the amplitude, we're taking it with respect to t. So we hold a constant, we just get the a, and then we apply the same rule. What's the derivative of cosine? Well, it's just going to be negative sine. right? And then same function for the inside, omega t plus phi, and we take the derivative of the inside function. So again, hold the w constant, or the omega constant, take the derivative of t. The derivative of t with respect to t, the derivative with respect to t of t is equivalent to, well, if you can imagine a power 1, bring the power down, you get 1 t, and then you minus 1, and then you get 0. So this is just equivalent to omega, and then obviously the phi is 0, right? You get a value of phi that's 0 because you're holding that constant. So now you can just rearrange the equation and write it as negative a sine, you could just write the omega first. Omega, this is typically how it's written in like textbooks and such. So yeah, just rearrange it and that's what you get. So now we can consider the second derivative of time, which is equivalent to the first derivative of velocity, which is equivalent to the acceleration as a function of time. And I'm going to consider that as the second derivative with respect to t of our original equation, a cos omega t plus phi. So really that's equivalent to the first derivative with respect to t of the function that we just derived with this one, negative a omega sine omega t plus phi, right? So the next thing we want to do is just do the same exact method. Hold amplitude and omega constant and apply the chain rule. So we get negative a, and then the derivative of negative sine is a negative cosine, so we get omega sine cosine, right? Because it goes back to the cosine, omega t plus phi, and again we pull out an omega, right? Because we're holding the omega and phi constant, and t is, we take the derivative of that, which is just 1. So if we simplify that, we get negative a omega squared cosine omega t plus phi. And that's your acceleration as a function of time. So really you can see how we can mathematically generate equations that describe simple harmonic motion. So I hope that helped. Bye.